Welcome students to this screencast where we're going to discuss function, linear or nonlinear. Again, this is Mr. Martin at Greenbrier Middle School. And if you remember some of our previous screencasts, we've talked about linear functions. Often linear functions are represented in some form like slope-intercept form, y equals mx plus b, or maybe even standard form ax plus, by equals c. So you could have slope-intercept form or standard form. But in either case, linear functions, the one major thing they have in common is they have a constant rate of change, okay, or a constant slope. Meaning, if I were to quickly just sketch something that resembles a linear function, so if I were to just draw a very rough coordinate plane here, or coordinate axes, so here's my x-axis and my y, and then I draw some linear function, there we go. Notice that as this function moves, say it goes over 1 unit, goes up a certain amount of units. It has a constant rate of change. I go over 1 and then up some distance. Go over another, up some distance. Over another unit, up some distance. That distance, okay, that we're going up, or the rise over the run, let's get rid of that there. The rise over run is constant. You have a constant slope or a constant rate of change. All right, the rise over the run is a constant value for linear functions. Now, not all functions have constant rates of change or constant slopes. In fact, there are many other functions that differ in quite a bit from a linear function. Notice we have something called an absolute value function, all right, where the parent function is y equals x, the absolute value of x. This here is not y equals the absolute value of x, but this is some transformation of that parent graph. And notice, it passes the vertical line test. If I were to draw vertical lines, they would only intersect one time. But notice it doesn't have a constant slope. Over here we're decreasing, and over here our slope is increasing. Over here it looks like the slope is about 1, over 1 in the positive x direction, up 1 in the positive y direction. But over here, as I move over 1 in the positive x direction, I actually have to drop 1 in the y, okay? So we have this decreasing slope and then an increasing. Here we have a quadratic function whose parent function or parent graph would be y equals x squared. Now this is not a graph of y equals x squared, but the parent graph is y equals x squared. Notice it has a decreasing rate of change, okay? And then increasing, okay? Decreasing, all right, and then increasing. So a negative slope, positive slope. And notice that as these approach their vertices or their vertex, okay, the slope, all right, here the slope is constant on this side, and then on this side it's constant, but it changes from a negative slope to a positive. Here on the quadratic function, the slope gets less and less steep until the slope is actually 0 at this point, and then it gets steeper. All right, so this slope gets more and more steep here, but it gets less and less steep on this side. So again, definitely not a constant rate of change throughout these two functions. And here we've got a cubic function whose parent, all right, equation, parent function is y equals x to the third power, x cubed. And again, you notice that this rate of change is not constant, okay? So let's take a look at a couple examples. Here we've got some function, and what I want to know is it linear or is it nonlinear? Now you may be able to look at this and say, hey, that looks a lot like my y equals mx plus b. But let's plot a couple points and just take a look. Let's look at the table, look at the graph, and let's see if this is indeed a linear function. I'm going to use values that are friendly with 1/2. So I'm going to use values that are divisible by 2 as input values. So I'm going to use -2, 0, 2, and 4. Now inputting these domain values into my function, 1/2 of -2 is -1. plus 3, well, that's 2. 1/2 of 0 is 2, or excuse me, 1/2 of 0 is 0, plus 3 is 3. 1/2 of 2 is 1, plus 3 gives me 4. And 1/2 of 4 is 2, plus 3 gives me 5. I'm going to go ahead and plot those points. So -2, all right, and 2, 0, 3, 2, and 4, and 4, 5. And I'm going to go ahead and draw the resulting linear function. Okay, there's the graph of that function. And if you notice, that is a line, that is a linear function. So we can go ahead and circle it. It's linear. Why? Well, its graph forms a line that has a constant rate of change. Notice that rate of change is a rise of 1 and a run of 2. Rise of 1, run of 2. Rise of 1, run of 2. And we get that right here. We see that our slope is 1/2. But also notice our rates of change here. Rate of change for the input, I'm adding 2 each time. That's constant. All right? And notice what's happening here. So my run is adding 2. What is my rise doing? Plus 1. So notice constant run, constant rise. This is a linear function. But now let's take a look at something else. Here I've just given you a table. And I've asked you to circle linear or nonlinear and explain why. Well, let's look at your input values. Is there a constant rate of change in your input values? Am I increasing these values? Notice they're increasing at a constant rate. Well, 1 to 3, what's the difference there? Well, the difference is 2. Added 2. How about 3 to 7? Well, notice that's a jump of 4, right? And notice 7 to 10, well, that's a jump of 3. So I do not have a constant increase here, or a constant rate of change in my input values. Well, that doesn't necessarily tell us it's nonlinear quite yet. Let's take a look at our output values, okay? So again, here's our domain. All right, our input values. Over here on the right-hand side, this is our range, our output values. Well, 2 to 4, that's an increase of 2, all right? Now, what we should expect is something different, because here I've got a large gap between 3 and 7, or at least a gap that's larger than the difference between 1 and 3. Notice the difference between 1 and 3 is 2. The difference between 7 and 3 here is 4. Well, notice the difference between 4 and 6, I'm just adding 2 again. And the difference between 6 and 10 here, I'm adding 4. Well, notice here, let's focus, and we don't even have to look at the bottom part of the table, but look right here. Notice my difference in my input values is different. All right, 1 to 3, that's a change of 2, but yet 3 to 7 is a change of 4. But my y values increase by the same amount. That means my slope is not constant. If I were to calculate the slope here, 4 minus 2, well, that's 2, over 3 minus 1, well, that's 2. That's a slope of 1. But notice if I were to try to calculate the slope between these two order pairs. All right, 6 minus 4, well, that's 2, over 7 minus 3, well, that's 4. That's a slope of 1/2. So the slope of the line passing through these 2 points is different from the slope of the line passing through those 2 points, meaning the slope is not constant. This is a non-linear function. Why? Because it does not exhibit a constant. And that's the key there, constant slope or constant rate of change. And I know that was a lot to pack into about 10 minutes, but the main goal here to understand is linear functions have a constant rate of change. Notice my rise is 2, my rise is 1, my run is 2. My rise is 1, my run is 2. My slope here is 1/2, rise over run. But here, I notice I calculated my slope using two different pairs of ordered pairs, and I got one slope to be 1, right here, positive 1, and then my slope between two of the other ordered pairs was 1/2. This table does not exhibit a constant rate of change, and therefore this is a nonlinear function. Thank you, and that does it for this screencast.